Good morning, friends. Today we will see detail about the data link layer. Okay, in previous lecture we will see how the sender and receiver machine can communicate with each other by sending and receiving the messages. Okay, uh, either wired or wireless. Okay, in wireless, air is used as medium. Okay, we already seen. Okay, in previous lecture, this is all about a position of data link layer, network layer. Second, okay, after physical layer, the data link layer is there, and after network layer is there. Onto the data link layer, network layer is there. Okay, uh, this already seen into the previous lecture. Okay, today is the last lecture. Now our syllabus is completed here. Okay, after we will see a physical layer coding violations. Okay, and error handling functions of timers. Okay, and this is a noise contaminates the binary signals. This already seen into the previous lecture. Okay, and how to detect and correct errors. Okay, error detection is a easy process, and error correction is a complex process that already studied in previous lecture. Afterwards, we will see the types of error. Okay, uh, there are two types of error. These are nothing but the content errors and flow integrity errors. This is also called a single bit errors or burst errors. Okay, uh, in single bit error only single bit can be changed, and burst error many types of bits can be changed. Okay, see here three bits are changed here, means 3 1001 and 10. Okay, and we will see a disadvantages of coding also in previous lecture. Okay, um, and redundancy. What is redundancy? Redundancy is nothing but the duplicate data. Okay, and with the help of parity check data. Okay, see in previous lecture we will also see about this, that is nothing but the structure of a transmitted code words. Okay, and each code word can contain two fields, that is data bits and a parity bits. Afterward, detection versus correction. Okay, we will see in previous lecture detection and correction of errors. Okay, are the two most important aspects of error control in data communications. The correction of error is more difficult, okay, as compared to the detection. And forward error correction versus retransmissions, this also seen in previous lecture, that is forward error correction and atomic request for transmission, that is FEC and error correction techniques. Hmm? That is forward error correction can gives a 3 out of, we have to choose a nearest. And retransmission, in this technique the receiver detects the presence of error in the received code words. Okay, and request the sender to resend that code word message again. Retransmission is repeated until the received message is error free. See here, these are the ARQ techniques, retransmissions. Okay, in there is explain the ARQ protocol. This type of university question is there. Then we have to explain the ARQ protocol, ARQ techniques. Okay, retransmission. There are two basic systems of error detection and correction. The first is being forward error correction. If this is nothing but the forward error correction system, and the second one is nothing but the ARQ, automatic repeat request. Okay, ARQ is nothing but the automatic repeat request systems. Okay, in ARQ system of error control, when an error is detected, the receiver makes a request to the transmission of that signals. Therefore, feedback channel is required for sending the request for retransmission. That's why it is also called as a automatic error control, because repeat again it can send the message or feedback to the sender machines. The receiver machine can send the feedback to the receiver machine. That's why it is called as an atomic request. atomic repeat request. That's why ARQ is nothing but atomic repeat request. See here, in ARQ system, less number of check bits, that is parity bits, are required to the send. Okay, this will increase the K of n ratio for NK block code if transmitted using ARQ system. Okay, a return transmission path and additional hardware in order to implement repeat transmission of code word will be needed. The bit rate of forward transmission must make allowance for backward repeat transmissions. This already we studied in previous lecture. This is a basic ARQ systems. Okay, this is a block diagram of the basic ARQ system. See a message input. This is a block diagram of basic ARQ system. Encoder is there. Encoder can input buffer and controller. Forward transmission channel, detector, output buffer and controller is there. Okay, and return transmission channels. This is all about operations of ARQ system. Just observe this block diagram of the basic ARQ system detail. And operations of ARQ system. The encoder products code word for each message signals. Okay, as its input, each code word at the encode output is stored temporarily and transmit over the forward transmission channels. At the destination, a decoder will decode the code words and search for errors. Okay, see, the decoder will send a positive acknowledgement. ACK is nothing but a positive acknowledgement if no errors are detected, and it will output a negative acknowledgement, NAK. ACK is nothing but a acknowledgement. NAK is nothing but a N means negative acknowledgement. If errors are detected, then it can send a NAK, that is negative acknowledgement. Okay, to the transmitter. On the non-transmission channel, on receiving a negative acknowledgement, NAK signals via a return transmission paths are controller with a retransmits the appropriate word from the word stored by a input buffer. Okay, a particular word may be retransmitted only once, or it may be retransmitted twice. Okay, number of times it may be transmitted. The output controller and buffer on the receiver side assembles the output bit stream from the code words accepted by the decoder. Okay, now the output controller and buffer on the receiver side assembles the output bit stream from the code words accepted by the decoder. See here, this is error probability on the return path. The bit rate of the return transmission, which involves the return transmission of acknowledgement signal, is low as compared to the bit rate of the forward retransmission. Therefore, error probability of the return transmission is a negligible. Small types of ARQ systems. Here, the three types of ARQ systems are there: automated return, stop and wait ARQ system, go back in ARQ, and select repeated ARQ. Okay, these are the three types of ARQ systems. Now we'll see coding. Okay, redundancy can be implemented by using a various coding schemes. The block diagram explains the coding and decoding process. Okay, at the sending end, redundant bits are added to data words using a well-defined process. The receiver detects and corrects the errors and make decision on whether to accept or discard the received message. The two most important factors in any coding schemes are as follows: ratio of parity bits to data bits and how robust the process is. Okay, the coding scheme can be divided into two types. These are nothing but a block coding and convolution coding. See here, this is a sending and this is a receiving end. Okay, sender end and receiver end. In sending end, data plus parity, data generated and data plus parity. Okay, unreliable transmission, this is a structure of encoding and decoding process. Okay, sending end and receiving end is there. Data, correct or discard the code words. Checker, received code words. Data plus parity, receive code words. Generator, checker. Data, finally sending and receiving it. Data generated, data parity and its unreliable transmission is there. Received code word, checker and data, correct or discard the code word and data. Finally you get a receiver get a data. Okay, whatever sender can send, no, that can be data on a receiver machines. That data can be get on a receiver machines. Okay, now we will see next is nothing but a modular arithmetic. Okay, modulo 2 arithmetic. In modular arithmetic, only a limited range of integer is used. The upper limit is defined as modulo n. Then the number of integers used are in the range 0 and minus 1 inclusive of both. Okay, addition and subtraction in modular arithmetics are simple as there is no carry when you add or subtract two digits in columns. This already we seen in a previous lecture, that is modulo 2 arithmetic also by XOR or exclusive or gates. Now linear blocklets, resource encoders, closed word structures, this all seen in the previous lecture. Afterward there are some solved examples. Parity check, this also seen in the previous lecture. Okay. See here, when does the parity checking fails to detect error? If the number of errors is introduced in transmitted code is 2 or any even numbers, then parity of the received code word will not change. It will still remain even as shown in figures. Okay, receiver will fail to detect the presence of errors. See here, this is a transmitted code and this is a received code with two errors, means 0 can be replaced with 1 and here again 0 is replaced with 1, means we can receive an error. Okay, this is a sender and this is a receiver. Receiver code can get two errors. Okay, even parity. If we get a same message without any error, see here conclusion, what we concluded here: double or any even number of errors in the received word will not change the parity. Okay, and therefore even number of errors will be unnoticed. Here we get a even parity, no error. Even if we get even parity, even change, then there is no error occur or no error will be unnoticed. Okay, if one or odd number of errors occur, then parity of the received word will be different from the parity of transmitted signal. Thus error is noticed, however this error can neither be located. Okay, now we see a limitation of parity checking. The simple parity checking methods has its limitation. It is not suitable for detection multiple errors, that is 2, 4, 6, etc. And the other limitation of parity checking method is that it cannot reveal the location of enormous bit. It cannot be correct error either. Okay, now see a simple parity check block code. See here, this is us in this table show the code words for parity checks code with k is equal to 2 and n is equal to 3. This is a data word and this is a code word 0 0 0 0 0. Parity bit has been encircled. 0 1 1 can be parity bit. 1 0 1 1 0. These are the see here. Whatever parity bit has been shown into the circle. Similarly, it is possible to write code word with k is equal to 3 and n is equal to 4. Here, see here, number of data words is n is equal to the number of data words. Okay, this second table can shows the code words for parity check code with k is equal to 3 and n is equal to 4. Means there are 4 data words, that is 0 0 0. Code word is 0 0 0 0. Data word is 1 0 0. Okay, 1 0 0 1. Observe this table. Okay, here are 4 data words, code words, data words and code words are there. Now we'll see encoder. Encoder means sender. Decoder means receiver, because decoder can decode the message. And okay, encoder means sender, because sender can encode the message. The encoder or sender for parity check code is shown here. The generator uses a data word as its input. 0 generates see here, the generator uses the data word as its input to generate a parity bit P0. Okay, the code word contains the original data words along with the parity bit as shown in figure. The parity bit P0 is generated by adding all the bits in the data words using modulo 2 addition, that is D0 plus D1 plus D2 plus D3 is modulo 2. The code word is then sent over the transmission media, over which it may get corrupted due to noise or corrected due to the when noise is added to the data, then that data may be corrupted. Okay, see here, this is encoder and decoder of parity check code. Observe this diagram carefully. This is the about encoder and decoder of parity check code. Sender is also called as encoder because sender can encode the message, and receiver is also called as decoder because receiver can decode the message. And these are the data words. Okay, D0, D2, D1, D0 here. On sender, encoder, generator are there, and decision logics are there, and checker is there on receiver. Transmission media. Encoder and decoder of parity check code. Now we'll see explanation of this diagram in detail. Decoder or receiver, the 5-bit code words corrupted by noise is received by the decoder. Okay, or receives as shown here. Here 5 bits, that is D3, D2, D1, D0, P0. Wait, I will open that page. Sender and receiver, there is encoder and decoder is there, no? See here, sender or encoder, decoder or receivers. Okay, sender can sender can use the generator, receiver can use the checker for the receiving message. The 5-bit code words corrupted by noise is received by decoder or receives as shown in here. The function of checker is same as that of generator with one change. It adds all the 5 bits mod 2 additions in the received code words and not 4 bits as in case of generator. The result of this addition is known as syndrome. It is a single bit produced at the output of the checker as shown here. The syndrome S0 is equal to 0 if the receiver code words has an even parity and H0 is equal to 1. If it is an odd parity, that is H0 is equal to D0 plus T1 plus T2 plus T3 up to P0. This syndrome is then applied to the decision logic analyzer. If H is not is equal to 0, it indicates an even parity, so there is no error in the received code words. Hence, the data bits of the received code words will be accepted. But if it's not is equal to 1, it indicates an odd parity, therefore an error is present in the received code word. Hence, data bit of the code words are discarded. Okay. Now a two-dimensional parity check, that is block parity. When large number of binary words are being transmitted or received in a succession, the resulting collection of bits is considered as a block of data with rows and columns as shown here. The parity bits are produced for each row and column such block of data. Two sets of parity bits are generated, known as longitudinal redundancy check and vertical redundancy checks. Longitudinal means horizontal and vertical. See here, this is a vertical and longitudinal parity. Just observe this diagram carefully. Okay, here vertical and horizontal parity checks are given. The vertical redundancy checks VRC bits and the horizontal LRC bits. There are 7 bits. This is a vertical, this is horizontal. See, this is a the following bit stream is encoding using VRC LRC. It is vertical and longitudinal and even parity. Locate and correct the errors if it is present. Afterward, Hamming codes. How, let us discuss other category of code, that is error correcting codes known as the Hamming code. Hamming codes are linear block codes. Okay, the family of n of k Hamming codes for d minimum is equal to 3 is defined by the following equation with the help of block length n is equal to 2 raised to m minus 1 and number of message bits, that is k is equal to 2 raised to m minus 1. Now see a number of parity bits n minus k is equal to m, where m is greater than 3, that is minimum number of parity bits is 3. The minimum distance, that is with the help of Hamming code we can calculate the minimum distance dm is equal to 3. This is a error detection and correction capability of Hamming code. Okay. The number of errors that can be detected per word is equal to 2, since d min is greater than equal to 5 plus s plus 1. Therefore 3 is greater than equal to s plus 1. Therefore s is less than equal to 2. Okay, the number of errors can be corrected per word is equal to 1. This is a Hamming code structure. Okay, Hamming code is basically a linear block code named after its inventor. It is an error correcting code. The parity bits are inserted in between data bits, okay, as shown here. See here in the first 7-bit Hamming code, this is a 7-bit Hamming code because this contains 7 blocks, and 15-bit Hamming codes contain 15, and here 1 2 3 this is a linear continuous blocks. 3 errors are occur, and here 4 errors are occurs. See the Hamming code word block diagram properly. After 7-bit Hamming code, a scientist named R.W. Hamming developed a coding system which was easy to implement. Okay, assuming that 4 data bits are to be transmitted, okay, he suggested a code word pattern shown here in the following. Okay, see here D7, D6, D5, D3, these are the data bits, and P4, P2, P1, these are the parity bits. Okay, this is a code word pattern for Hamming code. Means parity and data bits and parity bits combined together and form a 7-bit. Okay, selection of parity bits. Here bits to be checked, P1, P2, P3, P4 selected. This is the code word formats, the 7-bit Hamming code format shown here. Decide P1 and set parity of bits P1, P1, D3, D5. Okay, where D1, D3, D4 are nothing but the decide parity. Decide parity 1, decide parity 2. After decide parity 4. Okay, these are the sequential block or linear block diagrams of decide parities. See here are some example. Encode the data bits 0 1 0 1 into a 7-bit even parity Hamming code. Then we have to make 7 blocks here, 1 2 3 4 5 6 7, and d1 d2 d1 d2 d3 up to d, and we have to encode the data bits into 0 1 0. That's why I will write here 0 1 0 1. This is a parity of Hamming code. This is check the bits first of all and write the error words. Observe it carefully. Okay. Correct the error. Okay. Invert the incorrect bit to obtain the correct code words. Okay. Correct code words is equal to 100 1011. Now see here there are some solved examples. I will explain one examples. Okay, see here a 7-bit even parity Hamming code is received as 110101. What is the correct code? Okay, if here 7 7-bit even parity Hamming code is there. Okay, this is a received code 110101 because they given into the questions. Just write this into the linear block and check bit 4 5 6 7, that is 0 1 1 1, only parity, hence error. Set p4 is equal to 1. Check bit 2 3 6 7 or parity 2 3 6 7, means 0 1 1 1, hence error. Set p2 is equal to 1 and check bit 1357, only odd parity. Okay, first of all 4 5 6 7, afterward 2 3 6 7, afterward 1 3 5 7, hence no error. Set p1 is equal to 0. This can be set here, and the decimal equivalent of the error word is equal to 6, hence 6 bit is incorrect. Okay, get the correct code word as follows. This is a correct code word. These are the examples. A 7-bit Hamming code received is 111101. What is the correct code? That's why we have to first of all construct a linear block. Okay, assume even parity. Received code word is equal to this 111101. Check bits 4 5 6 7 is equal to 111. Even parity, so no errors. Check bits. This is all about the examples. See, so many solved examples, and consider the Hamming code for the data 1010 with odd parity. Means we have to consider about the odd parity. Okay, data word is equal to 1010 given. Okay, and so number of parity bits to be used is equal to 3 parity, because odd parity, no, that's why parity odd. The code word structure is as follows: 101 p4 0 p2 p1, because decide p1. See here, decide p1. In step 1, decide p1, consider bit in position 1357. 1357. The bits are 110 p1. p1 is equal to 1. Select p1 to have odd parity. Then decide p2. Consider bits 2 3 6 7. This bit are 100 p2. Okay, and decide p2. Consider bits 2 3 6 7. The bits are 100 p2. p2 is equal to 1. Select p4. Consider bits 4 5 6 7. The bits are 101 p4. Okay, and this is our write the code words. The code words is as follows: 100. This is a corrected. Okay, in step 4 corrected. This is all about the parity checks. There are some solved examples. Okay, this is all about Hamming code. Now performance of Hamming codes we will see into the next lecture.